Good day to all of you. I'm Joseph Barata. I'm here to discuss about my topic, the electrochemical power sources. The first subtopic is the Faraday's law of electrolysis. Michael Faraday conducted an extensive investigation of electrolysis of solution and melts of electrolytes. He was the first scientist who described the quantitative aspects of laws of electrolysis. He proposed two laws to explain the quantitative aspects of electrolysis, popularly known as the Faraday's law of electrolysis, namely first law of electrolysis and second law of electrolysis. The first Faraday's law of electrolysis, it is the one of the primary laws of electrolysis. It states during electrolysis, the amount of chemical reaction which occurs at any electrode under the influence of electrical energy is proportional to the quantity of electricity passed through the electrolytes, which is during the electrolysis, the amount of material that is subjected to oxidation or reduction of each electrode is directly proportional to the amount of the electricity that flows through the cell. It is equivalent to the current times the time product. The next, the next Faraday's law is the second law of electrolysis, which is the Faraday's law of electrolysis states that if the same amount of electricity is passed through different electrolytes, the masses of ions deposited at the electrodes are directly proportional to their chemical equivalents. The next subtopic is that the value of back EMF. For producing electrolysis, it is necessary that the applied voltage must be greater than the back EMF of electrolysis for the electrolyte. The value of this back EMF of electrolysis can be found thus. Let us, for example, find the decomposition voltage of water. We will assume that the energy required to separate water into its constituents, the oxygen and hydrogen, is equal to the energy liberated when hydrogen and oxygen combine to form water. Let hydrogen kcal be the amount of the heat liberated when the hydrogen and oxygen combine to form water. Let the H, which is the hydrogen kcal, be the amount of heat energy absorbed when the 9 kg of water are decomposed into 1 kilogram of hydrogen and 8 kg of oxygen. If the electrochemical equivalent of hydrogen is C, which is the zinc kilogram per column, then the passage of Q, which is the charge column, liberates the charge of the Z kilogram of hydrogen. Now, H, which is the hydrogen, is the heat energy required to release 1 kilogram of hydrogen, hence for releasing as referred to the standard hydrogen electron. These, the elements are assumed to be in normal solution, and, and at the atmospheric pressure, the, the charge of the Z kilogram of hydrogen, heat energy required is hydrogen times the Z charge kcal to G, which is the joule, hydrogen times the charge of Z, joules. If the energy is the decomposition voltage, then the energy is spent in the circulating charge column of charge is the energy charge per joule. Equating the two amounts of energies, we have this equation. Energy charge equals G times H times the charge of Z, or the energy time equals to G, which is the joule, times the hydrogen times the Z, which is the zinc, where J is 4,200 joules per kcal. The AMF of a cell can be calculated by determining the two electrodes potentials. The electrode potential is calculated in the same assumption that the electrical energy comes entirely from the heat of the reaction of the constituents. Let us take a zinc electrode. Suppose it is given that 1 kilogram of zinc which is dissolved liberates 540 kcal of heat and that electrochemical equivalent of Z is 0.338 times 10 to the power of 6 kilogram per coulomb. As calculated above, we have this solution. Energy equals J times H times Z equals to, which is the value of J is 4,200 times the value of the hydrogen, which is 540 times the electrochemical equivalent of zinc, which is the 0.338 times 10 to the power of 6, which is equal to 0.76 volts. So we proceed to the next subtopic, which is the primary and secondary batteries. An electric battery consists of a number of electrochemical cells connected either in series or parallel. A cell, which is the basic unit of battery, may be defined as a power-generating device, which is capable of converting stored chemical energy into electrical energy. If the stored energy is inherently present in the chemical substances, it is called the primary cell or non-rechargeable cell. Accordingly, the battery made of these cells is called primary battery. The example of primary cells are Lakeland cells, the zinc chlorine cells, alkaline manganese cells, and metal air cells, and etc. If, on the other hand, energy is induced in the chemical substances by applying an external source, it is called the secondary cell or rechargeable cell. A battery made of these cells is called the secondary battery or storage battery or rechargeable battery. Example of secondary cells are lead acid cell, nickel cadmium cells, nickel iron cell, nickel zinc cell, nickel hydrogen cell, silver zinc cell, and high temperature cells like lithium chlorine cells, lithium sulfur cells, or sodium sulfur cells, and many other more. This picture shows the primary battery and the secondary battery. The difference of these batteries are primary cells are ones which cannot be recharged and have to be discarded after the expiration of lifetime, whereas the secondary cells need to be recharged when the charge gets over. Both of these types of battery used extensively in various appliances and these cells differ in size and material used in them. Move on to the next subtopic is the classification of lead storage batteries. Lead storage batteries may be classified according to the service which they provide. The first is the SLI batteries, which is the supply power of engine starting and lighting ignition. The primary purpose of these batteries is to supply power, power engine starting, lighting, and ignition of vehicles propelled by IC engines such as automobiles, buses, lorries, and other heavy road vehicles and motorcycles, and many other more. Usually, these batteries provide 12 volts and consist of 6 series connected lead acid cells with capacity of the other 100 ampere per hour. Their, their present day energy density is about 45 watt hour per kilogram and 75 watt hour per cubic decimeter. These days, maintenance-free SLI batteries have been designed which do not require the addition of water. Throughout their normal service life of 2 to 5 years, MF version of the SLI batteries are constructed of such material that no gassing occurs during charging. In MF batteries, the electrolytes is either absorbed within the microporous separators, and the plates are mobilized with suitable sealing agents. These days, the SLI batteries are charged from the alternator, AC generator, and not from DC generator, dynamo DC generator. The alternating current produced by the alternator is converted into direct current by a full-wave bridge rectifier which uses semiconductor diodes. In this arrangement, no cutout is needed and transistorized voltage controller regulates the alternator output to suit the electrical load and the state of charge of the battery. The battery charged under constant voltage condition. This picture shows that the H2SO4 is the sulfuric acid. This is this one. As you can see in this photo. The lead grade pack with spongy lead anode, which is this one is this red one, and the lead grade pack with the lead oxide with is the PbO2 cathode. This is the yellow one. This is the example of the primary battery, and this is the example of the secondary battery. The next type of the next classification of lead storage batteries is the vehicle traction batteries. The recent universal concern over the levels of toxic gases, particularly in urban areas, emitted by the IC engines has revived interest in electric transaction. There has been great development in the use of battery-powered vehicles, primarily industrial trucks and commercial road vehicles of various types of uh, types like milk floats, for, for, forklift trucks, mining, tractors, aircraft service vehicles, electric cars, and more recently, in robotics and guided vehicles. Traction batteries are of higher quality than SLI batteries. They provide constant Let's continue. Traction batteries are of higher quality than SLI batteries. They provide constant output voltage, high volumetric capacity, good resistance of vibration, and a long service life. They can withstand prolonged and deep discharges followed by the deep recharges usually on daily basis. The voltage of traction batteries varies from 12 volts to 240 volts and they have a cycle life of 1,000 to 1,500 cycles. A number of advanced batteries are under development of EV use. The first is room temperature batteries like zinc nickel oxide battery, which is 75 watt hour per kilogram, and zinc chlorine hydrate battery, which is 80 watt hour per kilogram. And the second one is the high temperature batteries like sodium sulfur battery, which is 1,000 watt hour per kilogram, and lithium iron sulfide battery, which is 100 watt hour per kilogram. And next is the stationary batteries. Their use falls into two groups: A as standby power system and B as load leveling system. In the standby applications, the battery is used to power essential equipment to provide alarms or emergency lighting in case of breakdown in the main power supply. Standby applications have increased in recent years with increasing demand for uninterruptible power systems, and tremendous growth in new telecommunication network. The UPS provides clean AC supply free of shades or surges in the line voltage, frequency variation spikes and transients of modern computer and electronic equipment. Bank of Shell lead acid SLA standby batteries have been recently used in telecommunication system and for UPS applications. Recently, advanced lead acid batteries have been used for load leveling purpose in the electric generating plants. A 100 million watt per watt hour lead acid battery load leveling system could occupy a building 2.5 story high and an area of about 250,000 cubic 250,000 about the area of 250,000 square meter. The next one is the formation of plates and lead acid cells. There are, in general, two methods of producing the active materials of the cells and attaching them to lead plates. These are known after the names of their inventors. First is the Plante plates or form plates. The next is the pure plates or pasted plates. Plante plates, Plante process. In this process, two sheets of lead are taken in the immersed dilute H2 is for is the sulfuric acid. The current is passed into this lead acid cell from the dynamo or some other external source of supply. Then due to electrolysis, hydrogen and oxygen are evolved at anode. Oxygen attacks lead converting into PbO2, which is the lead oxide, whereas cathode is unaffected because hydrogen can form compound into Pb. If the cell is now discharged or current is revised through it, the peroxide coated plate becomes cathode, so hydrogen form and H combines with the oxygen and PbO2, which is the lead oxide, to form water as the lead oxide plus the hydrogen peroxide minus n is equals to the lead plus the hydrogen peroxide plus water. Sorry, this is water. At the same time, oxygen goes to anode, the plate previously unattacked, which is lead and reacts to form lead oxide. Hence, the anode becomes covered with a thin film of lead oxide. By continuous reversal of the current or by charging and discharging the above electrolytic cell, then the thin film of lead oxide will become thicker and thicker, and the polarity of the cell will take increasingly longer time to reverse. Two lead plates, after being subjected to hundreds of reversal, will acquire a skin of lead oxide thick enough to possess sufficiently high capacity. This process of making positive plates is known as formation. The negative plates, also made by the same process, they are torn from the positive to negative plates by reversing the current through them until the lead oxide is converted into sponge lead. Although the plenty positive are very commonly used for stationary work. Plenty negative Plenty negative have been completely replaced with a pure or pasted type plates, as discussed in Article 9:15. However, owing to the length of time required the enormous expenditure of electrical energy. This process is commercially impracticable. The process of formation can be accelerated by forming agents such as acetic, nitric, or hydrochloric acid or their salts, but still this method is expensive and slow, and plates are heavy. The next step is the Faure process. In the making of Faure plates, the active material is mechanically applied instead of being electrochemically produced out of lead plates itself, as in Plante Process. The active material, which is the form of red lead, the Pb3O4, which is the lead tetroxide, or it charged PbO, or the mixtures of the two various proportions, is pressed into the interstices of a thin lead grid or lattice work of intersecting ribs, which also serves as conductor of current. The plates, after being thus pasted, are allowed to dry and harden and unharden, are then assembled in weak solution of H2S4, which is the sulfuric acid, specific gravity to 1:1 to 1:2, and formed by passing an electric current between them. If plates are meant to be positive, they are connected up as anodes. If negative, then as cathodes. The oxygen involved at the anode converts the lead oxide to sulfuric acid, the lead oxide to lead tetroxide into peroxide, and the hydrogen re- reduces the lead to sponge lead by attracting the oxygen. The next subtopic is the positive pasted plates. Formation of positive plates involves converting lead oxide into PbO. A high lead oxide requires lead the Pb3O4 is the lead tetroxide used for economy both both in current and time, although in practice a mixture of lead tetroxide and the lead is taken, the latter being added to assist the setting or cementation of the plate. The next subtopic is the negative pasted plates. Pure process is much better adapted for making a negative rather than a positive plate. The negative material, sponge lead, is quite tough instead of being hard and brittle like the lead oxide, and moreover, it undergoes a comparatively negligible change in volume during the charging and discharging of the cell. Hence, it has no tendency to disintegrate or shed out the grid, although it does tend to lose its porosity and become dense and so lose capacity. Hence, in the manufacture of the pasted negatives, a small percentage of certain substances like powdered pumic or graphite or magnesium sulfate or barium sulfate is added to increase the porosity of the material. If properly handled, a paste made of H2 H2S4 is the sulfuric acid, glycerin, or the lead or mixture of PbO and PbO3 result in a very good negative because glycerin is carbonized during formation and so helps in keeping the paste porous. Pure plates, Pure plates are in more general use because they are cheaper and have a high capacity weight ratio than Plante plates. Because of the lightness and high capacity weight ratio, such plates are used practically for all kinds of portable service like electric vehicles, lightning, car lightning, and straightening and more other. But their life is shortened as compared to Plante plates. The next subtopics is I'm going to discuss is the internal resistance and capacity of a cell. The secondary cell possesses internal resistance due to some voltage is lost in the form of potential drop across in when current is flowing. Hence, the internal resistance of the cell has to be kept to the minimum. One, one obvious way to lessen internal resistance is to increase the size of plates. However, there is a limit to this because the cell will become too big to handle. Hence, in practice, it is usual to multiply the number of plate inside the cell and to join all the negative plates together all the one positive ones together as shown in the figure 9.11 this photo. The, the effect of equivalent to joining many cells in parallel at the same time, the length of the electrolyte between the electrodes is decreased with a consequent reduction in the internal resistance. The capacity of a cell is given by the product of the current in amperes and the time in hours during during which the cell can supply current until the EMF falls to 1.8 volts. It is expressed ampere per hour is this one. The interlacing of plates not only decreases the internal resistance but additionally increases the capacity of the cell. Also, there is always one more negat- negative plate than the positive plates. There is a negative plate at both ends. This gives us more mechanical strength but also assures the both sides of the positive plates are used. Since in this arrangement, the plates are quite close to each other, something must be done to make sure that a positive plate does not touch the negative plate, otherwise an internal short circuit will take place. The separation between the two plates is achieved by using separators, which in the case of small cells are treated cedar woods, glass, walnut, microporous rubber, and microporous plastic, and in the case of large stationary cells, they are in the form of glass rods. This one is the electrical characteristic of lead acid cells. The three important features of an accumulator of interest to an engineer are number one is the voltage, virtual capacity, and the efficiency. The first one is the voltage. The open circuit voltage our fully charged cell is approximately 2.2 volt. This value is not fixed but depends on an A line of the time since it was last charged. B the specific gravity voltage increasing with increase in speed gravity and vice versa. The speed gravity comes near to the density of water. What is 1.00, then the voltage of the cell will disappear altogether. It is shown in the figure 9.12. This is this one. This one is the cell voltage and this one is the time per hour. Shown in the graph, it is charging to make it to the fully charged, and this is discharging. The C is that temperature voltage increases through not much with increase in temperature. The variation in the terminal PD of a cell on charge and discharge are shown in the figure 9.12. This is this one. The voltage fall depends on the rate of discharge. Rates of discharge are generally specified by the numbers of hours during which the cell will sustain the rate in question before falling to 1.8 volts. The voltage fall rapidly beginning in the beginning rate or fall depending on the rate of the discharge, then vary slowly up to 1.8 and again suddenly to 1.85 and then suddenly to 1.8. The voltage should not be allowed to fall to lower than 1.8 volt, otherwise hard insoluble lead sulfate is formed in the plate which increases the terminal resistance of the cell. The general form of the voltage time curves corresponding to 1 minus to 3 minus 50 and 10 minus R rates of corresponding to the steady current which would discharge the cell in the above mentioned time in hour. It will be seen that both of the terminal voltage and the rate the rate at which the voltage and the rate at which the voltage falls depends on the rate of discharge, and more rapid fall in the voltage is higher rates discharge due to the rapid increase in internal resistance of the cell. During charging, the PD increases shown in the figure 9.12 is this one. The curve is similar to the discharge curve reverse but is everywhere higher due to the increased density of H2A source, the sulfuric acid, and in the pores as is shown in the figure 9.13 of the positive phase is this one. This one is the time of discharge in hours and this one is the voltage per cell on load. As you can see, it's the volts per cell is going up. The minimum permissible volts will going will slowly going up also and it's time consuming. The next one is the capacity. It is measured in amperes per hour, amp hour. The capacity is always given at a specific rate of discharge is 10 hour discharge in UK in UK. 8-hour discharge in USA. However, motorcycle battery capacity is based on a 20-hour rate at 30 degrees Celsius. The capacity depends upon the following. Rate of discharge. The capacity of a cell as measured in amp hour depends on the discharge rate. It decreases with the increased rate of discharge. Rapid rate of discharge means greater fall in PD of the cell due to internal resistance of the cell. Moreover, with rapid discharge, the weakening of the acid in the pores of the plates is also greater. Hence, the chemical change produced at the plates by 1 ampere for 10 hours is not the same produced by the 2 ampere for 5 hours and 4 ampere for 2.5 hours. It is found that a cell having a 100 amp hour capacity at 10-hour discharge rate has its capacity reduced to 82 amp hour at 5-hour rate and 50 amp hour at 1-hour rate. The variation of capacity with discharge rate is shown in the figure 9.14, which is this one. B is the temperature. At high temperature, chemical reactions within the cell take place more vigorously. The second is the resistance of the acid is decreased, and the third is there is a battery diffusion of the electrolyte. Hence, high temperature increases the capacity of the lead acid cell. Apparently, it is better to operate the battery at a high temperature. However, at the high temperatures, the acid attacks the antimony lead, alloy grid, terminal post, or wooden separators. The, the paste is rapidly changed into the lead sulfate. Sulfation is always accompanied by expansion of phase, particularly at the positive plates, and results in buckling and cracking of the grid. Hence, it is not advisable to work batteries above 40 degrees Celsius. As temperature is lowered, the speed of the chemical reaction is decreased. Moreover, cell resistance also increases. Consequently, the capacity of the cell decreases with decrease of decrease in temperature till at freezing point the capacity reduced to zero even though the battery otherwise be fully charged. Perceive it is the density of electrolyte. As the density of electrolyte affects the internal resistance of the and the vigor of chemical reaction, it has an important effect on the capacity. Capacity increases with the density. The quantity of effective of the quantity of active material. Since production of electricity depends on chemical action taking place within the cell, it is obvious that the capacity of the battery must depend directly upon the kind the kind and amount of the active material employed. Consider the following calculation. The gram equivalent of lead is 103.6 grams and Faraday's constants is 26,500 coulombs, which is 96 96,500 divided by 3,600, which is equal to 26.8 amp per hour. Hence, during the delivery of 1 amp hour by the cell, the quantity of lead expended to form lead sulfate at the negative plate is 103.6 divided by 26.8 is equal to 3.86 gram. Similarly, it can be calculated that at the same time 4.46 gram of lead oxide would be converted into lead sulfate at the positive plate, while 3.66 gram of acid would be expended to form 0.672 gram of water. It is obvious that for obtaining a cell of a greater capacity, it is necessary to provide the plates with larger amounts of active material. So that's all for my report. Hope that you understand and thank you. And good day also.